Hello and welcome back, and thank you very much for watching this lecture video. In this lecture, we will be talking about Baeyer-Villiger oxidation reaction. Is a reaction that it will take an aldehyde or a ketone molecule and it will transfer it to carboxylic acid or an ester molecule. So it depends what you start with. If you start with an aldehyde product, it will be molecule with a carboxylic functional group or COOH. And if you start with ketone, you will get COOR or ester molecule. And for aldehyde, we get this functional group. And for an ester, we get the carbonyl, but the carbonyl is attached to O and O attached to R, and R, it can be anything. Okay. And in order to run such a reaction, we need to have a peroxy acid. And what's a peroxy acid? Peroxy acid, if you take, let's say you have an alkyl group, and that alkyl group attached to a carbonyl, and the carbonyl is attached to oxygen, and that oxygen is attached to another oxygen. And now we have a hydrogen atom. And so we have two oxygen atoms attached to each other through a single bond. And remember that any of those oxygen atoms, it has two lone pair. And if you have a carbonyl and two oxygen atoms attached to each other, that means you're dealing with a peroxy acid. And anytime you add a peroxy acid to any double bond or triple bond, and be aware that you are inserting oxygen to the system. Okay, you are inserting oxygen to the system because O bond is not that stable bond. And the most common peroxy acid is methylchloroperbenzoic acid. And the structure for it, okay, we have a benzene ring, and say you have a carbonyl group, and the carbonyl is attached to oxygen, another oxygen, and now hydrogen. So that's going to be the perbenzoic acid until now, the functional group of the perbenzoic acid. But it says metachloro on here we have ortho, and then meta, in the meta position we have a chloro atom there, and that's going to be the most common peroxy acid that we use it in chemistry. And the reaction is going to start with addition of terminal oxygen to the carbonyl. And remember, the carbonyl has a carbon that is electrophilic, so it's looking for technically electron or a lone pair, and that's going to give us oxygen with a positive charge. What will happen with the pi bond? The pi bond, it's going to move on the oxygen of the carbonyl group, and now we have oxygen with a negative charge, the oxygen of the carbonyl group, and oxygen that came from peroxy acid, it has a positive charge. And next step, we will have interaction between the carbonyl of the peroxy acid and hydrogen atom, and it will take hydrogen atom from it, and technically it will stabilize that oxygen. But the cause for it is having a positive charge on carbonyl, technically on oxygen of the carbonyl. Which carbonyl? The carbonyl group of peroxy acid. Now, next step, oxygen with a negative charge is going to share a lone pair, and a lone pair with carbon, and so that means we can actually kick something out of the system. But before that one happen, we will have a rearrangement, or it will rearrange one of this R, and it will move. And I'm going to highlight that one. Say that R is going to move, and it will attach oxygen, and while get it inserted to oxygen, and second oxygen, it will leave the system, and this one it will live as technically like O with a negative charge, and that's gonna that's gonna give us an acid, and it will give us carboxylic acid. Now what will happen with this section, this one, that's gonna give us ester molecule. And remember, we started with a ketone molecule, so we're gonna get an ester molecule. And okay, now I want to know what will happen if I start with, let's say, for example, aliphatic ketone or cyclic ketone, what type of product I'm going to get. Okay, the first thing that you need to do, highlight the alpha carbon. And this is the alpha carbon, and that one is the alpha carbon. And are they identical? Let's see. We have two substituents attached to the carbonyl group, and both of them are identical. So doesn't matter where to put oxygen, left, right. Should I put oxygen here or there? No, honestly, it doesn't matter. It will give you the same product. So the product that I'm going to get, it will be something like this. I will have the carbonyl group here. That's O. Now I will have oxygen. Oxygen get inserted. And now I'm left with the ethyl group. And the ethyl group, I'm going to draw it here. So I just simply added oxygen to the system. And because those two alpha are identical, it doesn't matter where you put the oxygen. And again, we have two alpha position, and both of them are identical. And so I'm going to say then, like the thing that is going to happen, the peroxy acid, it will insert oxygen, and oxygen, it can be here or there. Okay, so the product that I will get, instead of 5 members, this time I'm going to get 6 members. So I will have a carbonyl group. That carbonyl group, it will be attached to oxygen. And so I have a carbonyl group that's attached to oxygen on one side, and that oxygen also attached to a carbon. So I have an ester, technically, molecule. And from 5 members of a ring with 5 members, I got a ring with 6 members. So the ring got bigger. That means the ring is going to be more stable. Now, what will happen if the alpha positions or alpha carbons are not identical? And in that case, how should I, predict the product? Go with this trend that's, like you need to have something to stabilize, the positive charge. Remember, we get a positive charge here. We get a positive charge on oxygen, and we said, like, if we can't stabilize that positive charge, or delocalize it, the system, it will be happy. Or how about this? If there is a group that it can donate electron density to oxygen, then positive charge, it will be neutralized by electron density from electron donating group, and the system will be happier. And hydride, not hydrogen, hydride is a good source of electron density, a small molecule, but a small atom with huge amount of electron density. If you can move hydrogen, hydrogen as hydride, then go with that one. Next step is the tertiary, because tertiary is more capable of handling the positive charge. Next one will be secondary or phenyl. Both of them, they will have almost the same, effect. And next, phenyl, it will be better than the primary, and the primary better than the methyl, technically carbon. Let's practice some example. I have a carbonyl group that attached to methyl group and isopropyl. So I'm going to say this one is alpha and that one also alpha. Now this one is going to be, this carbon is going to be a tertiary carbon. Well, this one, it will be a primary carbon. And we said the tertiary is more capable of handling the positive charge. So that means that you should put the positive charge, you should put oxygen here, not there. Okay, put oxygen between the isopropyl group and the carbonyl. And so that means that you're going to get such a product. And oxygen will be inserted. And then I get carbonyl, this carbonyl attached to CH3. So that's a molecule that I will get. And next one, I have hydrogen atom versus phenyl. We said go with this order: hydrogen, then tertiary, then secondary or phenyl, then primary, and then methyl. And because I have hydrogen here, or like I should say hydride, it will get a priority. That means that you should insert the oxygen here. And this is an aldehyde molecule. Because it's an aldehyde molecule, it should give you carboxylic acid. So I have a phenyl ring attached to a carbonyl. And now I will insert oxygen there. And I have hydrogen, and this is going to be a carboxylic acid. Well, that one was ester molecule because we started with a ketone. Okay, last one. Okay, we just practiced this example, and we have a ketone, okay, or a carbonyl group that attached to cyclopentane, and the 2 alpha are identical. And the only thing that I did, I just added a substituent. I added a methyl to one of the alpha carbons. So now I have alpha here and alpha there. This one is a secondary, while that one is a tertiary carbon. And we said the priority, it will go with the tertiary. What does it mean? It means you should insert oxygen there, put oxygen here. So I will get this, I will have a carbonyl group. Next step, we insert oxygen. Now oxygen, it will be attached to a carbon. That carbon is attached to a methyl. And so size of the ring from 5 member went up to 6. And as you see, the carbon that I'm going to highlight, this carbon is the one that attached to oxygen. And so oxygen was inserted to the right side of the molecule other than the left side, because we have a tertiary versus a secondary.